Welcome to the latest lesson in our series on relativity. This time we are going to focus on the relationship between the Earth and the ether. So to do that, first we need to talk about waves in general. Then we need to talk about the ether as it was proposed, the problems that came up as a result of the ether, and which lesson or lessons we'll be going on to next. So first, waves in general. So as far as people were concerned, at least around the time we're talking about in the late 19th century, anything that moved energy from one place to another was either a particle or a wave. Particles were the ones that had mass, they're physical objects. Waves are disturbances that carry energy through a medium that has mass, but they have no mass themselves. So, particles could not just be a single particle as we know it. The atomic model didn't exist yet as we know it. Particle could be a baseball. It's something you could touch, whereas a wave was more like a water wave. It can move energy from one side of a pond to another, but the water has to be there. Other options would not be considered until after the theory of relativity was published. So while they exist, they were not a factor in this conversation. Now the ether, which is sometimes spelled with an A in front, sometimes not. So the thought with the ether was that because waves required a medium to go through, at least in the classical model, and in the vacuum of space there was no medium, they figured that the light coming from the sun to the earth would have to have some sort of medium to pass through. So Christian Huygens proposed ether to fill this void in 1690. Planets must move through this medium, but they don't seem to have their orbits altered very much. We don't see a lot of lag in one way or the other. So light should speed up or slow down going through this ether because we don't see a big change in planets. They figured it has to be highly elastic, but very low density. Now, what problem was there with this classical model? Well, Michelson and Morley designed an experiment to measure the speed and direction of the ether relative to the solar system. So they figured if they could figure out where this ether was, they'd have a better understanding of how the universe worked. They actually had a very clever design. So they would take two perpendicular beams of light and look at the differences in speed as they traveled along those paths. They would repeat the experiment throughout the year to account for Earth's orbital motion. And then they would look at the net result and figure out, well, whatever they can account for because of Earth's orbit has to be because of the ether. The problem was that there was no relative difference in speeds detected. It was almost as if all beams of light move at identical speeds no matter what. They can go in any direction relative to this ether and come back as though they moved at identical speeds. They actually could not produce what's known as the interference pattern that's required to make this work. So, up next, if you are just going with the conceptual playlist, then you're going to see your next video is the problem with currents. If you're going through the complete playlist, then you're going to see first a video about how we calculated the speed of sound classically. And then second, we're going to look at the math behind the Michelson-Morley experiments. Once we've gone through those two lessons, then we will move on to the problem with currents that'll be next in the conceptual playlist. So those of you who have subscribed will see updates to the complete playlist before we see updates to the conceptual one.